Today we will be factoring GCFs, factoring special patterns, and factoring by grouping. We will be able to factor the GCF out of a polynomial. We will be able to factor special square and cube patterns, and we will be able to factor by grouping. So factor, the verb, so to factor is to rewrite as a product of expressions. Remember, product means multiply, so we'll have two or more things being multiplied together. Factor as a noun or a factor is an expression that divides evenly into another. And remember that expression can be numbers and variables. Or it could be just a number or just a variable. GCF stands for the greatest common factor. So GCF. So how do you factor a GCF out of a polynomial? We divide, and it will look like undistributing. So it's basically like distributing backwards. So in our first example, the first thing we need to do is figure out what the GCF is. So looking at the numbers first, 15, 20, and 10. The largest number that divides into all of them would be 5. Then we have an x cubed, an x to the 6th, and an x to the 4th. The thing that all of them have would be x cubed. And then for our y's, we have y squared, y cubed, and just y. So we can only take a y away from all of them. So we're going to divide all of them by this GCF. And since we're undistributing, the 5x cubed y goes out front, and what we get after we divide goes inside. So 15 divided by 5 is 3. We had x cubed, we divided by x cubed, so those canceled out. We had y squared divided by y, which basically means there was 2 y's here. We divided one out, so there's 1 left inside. Plus 20 divided by 5 would be 4. We had x to the 6th. We divided out x to the 3rd, so we're left with x to the 3rd. We had y to the 3rd. We divided out a y, so we're left with y squared. Negative 10 divided by 5 would be negative 2. We had x to the 4th. We divided out x cubed. We're left with an x. Y divided by y is 1, so that part's just gone. So there, we factored out the GCF. In our next example, we have 3, negative 12, and 9, and the thing that goes into all of those is 3. The first two terms have a's, but because the third one does not, we can't take out any a's. And the second and third terms have b's, but the first one does not, so we can't take any b's out. So our GCF this time is just 3. So I'm going to divide all of them by 3. My GCF goes out front, and when I divide, I'm left with a squared minus 4ab plus 3b squared. Now let's look at some of the patterns. First, our pattern for squares. So these all have a squared in them. You can only factor the difference of two perfect squares. Remember, difference means subtraction. So a squared minus b squared can be factored. A squared plus b squared cannot be factored, therefore it is prime. When we factor a squared minus b squared, it will factor to a minus b times a plus b. So basically we're going to take the square root of a, square root of b, square root of a squared, square root of b squared. That'll give us our a and b to plug in. So if we have 4x squared minus 121y squared, a would be the square root of 4 is 2, the square root of x squared is x. For b, the square root of 121 is 11, and the square root of y squared is y. So this would factor to 2x minus 11y and 2x plus 11y. X to the 8th is a perfect square because it is x to the 4th squared, and b, the square root of 256, would be 16. So if we factor this, we'd have x to the 4th minus 16 and x to the 4th plus 16. But now we have two perfect squares again being subtracted. So x to the 4th is really x squared squared, and the square root of 16 is 4. So we'd have x squared minus 4 and x squared plus 4, and then I'm going to bring down my x to the 4th plus 16. But look what happens now. X squared minus 4, that's another set of perfect squares being subtracted. So this time we'd have a is x and b is 2. So we'd get x minus 2 times x plus 2, bring down our x squared plus 4, and bring down our x to the 4th plus 16. And that's our final answer, because we've run out of perfect squares. As for 25z squared plus 9, these are all perfect squares, but it's not the difference, so this is prime. Now for our cube pattern. We can factor the sum or the difference of two perfect cubes. And the patterns are basically the same. So a cubed plus b cubed is a plus b times a squared minus a times b plus b squared. So the first sign is the same as the sign there. The second sign is the opposite. The third sign, the final sign, is always plus. So if we look at a cubed minus b cubed, it's going to follow the same idea. A minus b, a squared plus ab plus b squared. So the first sign matches the sign that was given. The second sign is opposite of what was given, and the third sign is always plus. So same, opposite, always plus. So when you're factoring cubes, make sure you use SOAP, S-O-A-P. So now we need to know our cubes. So what cubed gives me 8? That would be 2, and then our W, and B. 3 cubed is 27. So if we plug this into our pattern, A plus B times A squared, we need to square both things, so that would be 4W squared minus A times B would be 6W plus B squared would be 9. Now, in the second one, 2's not a cube and neither is 250. What we have here is a GCF we need to take out. So if we factor out the GCF of 2, we'd be left with Z cubed minus 125 Q cubed. And now we do have perfect cubes. A would just be Z and B would be 5Q. I'm going to ignore this 2 for a little bit and then I'll bring it back in at the end. So ignore that. So I would have Z minus 5Q for my A minus B. A squared would be Z squared plus A times B, so Z times 5Q would be 5QZ or 5ZQ. The order of the letters doesn't matter much. Typically we write them in alphabetical order though. Then plus B squared, we need to square both of these, so 25Q squared. Then that 2 we had out front we'll bring down. So this is for the sum or difference of 2 perfect cubes. So we're only going to have 2 terms at the beginning. Sometimes we have a cubic that has all 4 terms. It's got our x cubed, our x squared, our x, and our coefficient. So we're going to group pairs of terms, then factor the GCF. So group the first 2, group the second 2. These 2 have 6x squared in common. When I divide that out, I'm left with x plus 3. 15x and 45 have 15 in common. So x plus 3. But now we have this term and this term. What do they have in common? Well, they both have an x plus 3. So if I factor out x plus 3, then I'm left with 6x squared plus 15. But what do you notice about 6 and 15? They have a common factor of 3. If I divide out 3, we typically write that out front, I'd be left with 2x squared plus 5. And that's my final answer. And our final example, group the first 2, group the second 2. The first 2, I'm going to take out x squared, and I'll be left with 2x plus 1. Since we want what's in these parentheses to match, and we have 2 positives here. Up here, we're starting with 2 negatives, and that's a hint that we're going to factor out a negative number, and they're both divisible by 9. And if we divide these by negative 9, we will get 2x plus 1. So in common, they have a 2x plus 1, and we'd be left with x squared minus 9. But wait, that's a difference of perfect squares. We know how to factor that. So that would factor to x minus 3 and x plus 3, and then bring down my 2x plus 1. That's all for today. Fill in your summary, and I'll see you in class.